My favorite stuff. I love this. It is very true. So yesterday, I don't remember exactly where we ended our conversation because the bell just interrupted me, I'm sure, and it was annoying or whatever. So I know for a fact, you didn't? Okay, well, I wasn't planning to pour water on you intentionally, at least today. All right. So, no, we're done. All done. Okay, so yesterday we had a water in a cup, and we had a string, and we did some whirling of the water. Oh, yes, of course. I'm sorry, darling. There you go. And we came to this conclusion, and I don't remember if we got any further. Did we write anything more down than this, or was this it? No, that's all. That's all we had. Okay, so we've got some work to do. So we said by the end of the period, then that at the bottom, the cup with water in it had two forces that were acting in opposite directions. We said, and I just want to make sure you're okay with this, because it's weird. We said that if we have a cup with water in it, and we hold it like this, that there are two forces acting and they're both pulling down. Right? Is that what you're telling me? And you're telling me then that if Harrison lies on the floor, and who else was it? Was it? Kate. Oh, it was Kate, yeah. She was lying on the floor, and I was holding a cup up like this with water in it. And that water did not fall. And I don't know if I've told you, that for about 8 years of my 10 years that I was in Des Moines teaching, I taught with one of the best chemistry teachers that I've ever met. And not only was he an AP chemistry teacher, but he was also a professional magician. Have I told you this?
No.
Like professional magician, like legit. He was like the president of the Iowa Magicians Guild. Like, for real. Like, this guy was good. And here's the problem with that, is that all of my students would take AP Chem first, and then they'd come and take AP Physics with me. And so then when I would do things like regular physics with them, they'd be like, they think that I was doing all these tricks, right? Like, oh, that wasn't really water. Like, you had some sort of something in that. Like, they always thought I was doing tricks. I'm like, really, it's just, like, this is just physics. And now, I don't know if Alexon has some sort of other, like, hidden life where she's also a magician. I've never learned that about her. But what I want to be clear with is that I am not a professional magician. Like, I am a physicist, and that's what I do. So I need to be getting, like, understanding for why you have two forces that are both pulling down. And did you get wet?
No.
No.
But is water wet?
And we're not going there. Because it doesn't matter. All I want to know is, did the water fall out of the cup?
No.
It did not. Why not? Because the velocity of the water was, what did you say?
Because it was moving in a circle, and the velocity of the water wasn't moving.
So circular motion.
So there's circular motion involved. The water was moving. It was moving in this direction of this purple arrow. And I want to be very clear when you draw this on your picture that you label this as a velocity and not a force. And so if on a test, for example, you were asked to draw the forces acting on the water cup system, you would absolutely not draw this purple arrow. Are you with me there?
Yep.
Because that is not a force. There is no force acting in this direction. There is no force acting up either. Now, gut feeling, I want to know because, there's no shame in this. I'm just curious. When I first asked you to draw that free body diagram of the cup up here, before you talked to your teammates, before you really applied physics, how many of you wanted to put an arrow going up? Did ya? It's okay, because most people do. Because the water is not going which way? Down. It's not going down. So there's got to be something holding it up, right? That's what your logic tells you. But the physics says that's not the deal. It has to do with this velocity, right? We know that if there's no net force, which is what you had told me way down here. Now, that argument changes a little bit when we start moving, but I'm going to ignore that for a second. Down here, when we first started, there was no force. No net force means that there's no acceleration, right? Life is good. So an object that's not moving, if there's no acceleration, let me just write this down. If the acceleration equals 0 and the initial velocity is 0, then that means what about the final velocity? Not a trick question, friends. It's 0, right? But at the top, if the initial velocity isn't 0 and there's no acceleration, that means that the final velocity would be the same thing, right? It's going to be the same thing. Whatever that not equal to 0 is, the final velocity is equal to that initial velocity. This is just Newton's first law, Newton's first and second law, really. Like, that's all it is. This water, if I had happened to cut this string, where would this water have gone?
You cut it. What?
Like, I cut the string right here.
Right now. When it's at the top.
When it's up here.
Yeah.
Where's it going to go? It's
Up.
going to go out, and then we're going to go back to chapter 2 and do projectile motion. Are you with me there? Yeah? Okay. So, yeah, it would do that. It would just want to follow normal physics, blah, blah, blah. But the trouble is that string is pulling it in. You with me there? Okay? So in this case, at the top, right up here, we need to make some notes and we need to write this down and kind of get this in our brains here. At that point right there, the acceleration does not equal 0. In fact, what direction is that acceleration pointing in? It's pointing down. Are you with me there? It's pointing down. The net force is down. And that means that the water cup system is accelerating in what direction? Down. Okay? Okay? Which means that the water is being prevented from going in the direction it wanted to go in. So, full disclosure from many years of being a physics teacher, this is not the first whirling water cup that I've ever made. I don't know if when you were a kid you ever used Dixie cups or these kind of like wax-covered cups and left some water or something in them for a while and left it there for a while. Have you ever done this? And then the wax seals kind of get gross and they get a little messy and they stop being nice and waterproof. So I used to have a cup like this. Looked very similar, I think. Okay, and accidentally it was probably a Friday afternoon that I did this demo, and then I left for the weekend and forgot to pour the water out. And then I came back the next day, and I just dumped the water, or the next Monday, I dumped the water out, went about my business, and the next year or week or month or whenever I needed to do the demo again, got it out, and then I had some kid lay on the floor, right?
Oh my God.
And no, it's not as bad as you think. I need to make that clear. It's not as bad as you think, but instead of this nice waterproof seal, the water was able to seep out a little bit. And so then I'm like talking, I'm doing my thing, right? Oh, you're not getting wet. And the kid's like, yes, I am. I'm like, no, you're not. Like, stop lying. Like, maybe that's like sweat, blah, blah. Like, I was trying to like play it on. He's like, no, like I totally am getting wet. And I was like, oh. What was wrong?
Physics.
That's the wrong answer.
Physics lie.
What was wrong?
It wasn't
There was not a force, right? So if you think about this as the cup water system, you've got the string down and you've got the gravity down. But if you think about just the water itself, what's holding the water inside the cup? What's pushing on the water, pushing it down?
The bottom.
The bottom of the cup, right? And so if the bottom of the cup is not, like, it's not made with fidelity, it's got leaks in it, then that water that is moving at a constant rate of speed, what does that water want to do? It just wants to keep going. And then, my student that had his head right here was like, I'm totally getting wet. Oops. I mean, it wasn't like I was dumping water on him, but, like a little bit. He got a little bit wet. And, we all learned a lesson from that. All right. We doing all right so far? Okay. So we're going to do this. We're going to kind of switch from this to a horizontal situation. And the reason that I like horizontal situations is that it gets rid of gravity as a problem. So here we go. We're gonna move on just a little tiny bit here. I'm gonna draw myself a new circle, and you can go ahead and draw yourself a new circle as well. Okay, oops. Draw a circle. Right? How's your circle looking there? You just
It's actually multiple strands in the work.
Can you breathe there?
All right. So I would like you to draw a circle. Now I'll tell you what this image is, and we're not going to do this demo because I think you've got it. I think you understand it. We don't need to all get up and move around. We just need to talk for a second. So here's the situation. I've got a yo-yo in the back. It's from the Dollar General, so it's like not a good yo-yo. It's just a piece of plastic on a string, and that works well for what I'm doing. And I'm going to take that yo-yo, and in your imagination, you're going to imagine that I'm going to spin that yo-yo around on the floor. Okay? Now, as I spin that yo-yo around on the floor, if we drew a free body diagram of the yo-yo, so here's the floor. This is like the side view, right? And here's the yo-yo sitting here, and then the string pulling it in. And it's going around, so it's maybe coming out of the page. Are you with me here? That's the floor. That's the yo-yo spinning around this way. What forces are acting on the yo-yo?
Force of gravity.
Force of gravity. Which way does that one pull or push?
Down.
Down towards the center of the earth, right? It's going to go down, down. Here it goes. Down it goes. I'm just going to call it FG because we're trying to go fast. What else you got?
Force of tension.
Force of tension. Which way does that one go?
Perpendicular.
Perpendicular what?
Just perpendicular.
Perpendicular to what? Maybe I should ask it that way.
Yo-yo.
I mean, the
Force
yo-yo's
the
good.
earth. Force the earth. Yeah. Right.
Okay, and so maybe more, can we kind of ask you to think a little hard? You mean this way, right? Is that what you meant, Henry? I don't want to put words in your mouth.
Yes, that's what I meant.
Okay,
I said perpendicular. That's what I meant.
you did, and that's right. I just wanted to make sure that I was communicating with you because one could argue that there are multiple perpendiculars. The more, so I'm going to help you out here. So if you were answering that question again, and you're trying to answer for a direction of attention, you could say along the direction of the rope. You with me there?
Yes.
Yeah. So just like, just kind of thinking outside the box there. Along the direction of the rope, life is good. Any other forces acting on that yo-yo?
Air resistance?
Air resistance is not it. What else is acting on it? It's sitting on the floor, and it's going around and around and around.
It's already covered.
Something with spin.
It's touching the floor. Yep.
That was levitating.
No, that's too fancy.
That's actually falling through the ground. The vectors aren't equal.
There you go. Is that better?
They're still not equal.
Shush your mouth. You draw yours nicely. How do these two compare? I have to get through stuff, friends. We have May, what is it? May 7th, May 9th, whatever it is. It's not, we got to get there. How do these two forces compare? How do you know?
Because there's no acceleration, so F equals 0.
No acceleration in this direction, right? Boom. We good? Okay.
Is there friction?
Is there friction? No, we're going to assume no friction because frictionless floor makes it easier, right? I mean, one could do it, but it takes a lot more work. We don't want to do that. So we're going to say that Fn plus Fg adds to 0. So in the vertical direction, F net is 0. Talk to me about the horizontal direction, though. Is the F net 0?
No.
It is not. It is not. Now we're going to look at just that part, okay? So let's take a look up here. So we got the tension force. It's pulling in this direction, right? Okay? Can you draw the tangential velocity, the velocity of that yo-yo right at this moment? Yes is the answer. Go ahead and do it.
That's not velocity.
That is the velocity.
Oh, I thought you wanted the exact velocity. That's what
No.
I said no.
Gotcha. Okay.
Makes sense.
That is a velocity. That's a right. No, I said you have to. You just.
A little while later, your yo-yo is here, yeah? A little while later, the tangential velocity is here. Is that ball changing speed necessarily?
No, man.
But is it accelerating?
Yes, ma'am.
Yes, it is. Yes, it is.
You have to.
The object, the yo-yo in this case, is accelerating. Okay? Because it's what? Yeah. Okay. Tell me about the direction of the acceleration. What'd you say, Ian? No, you did say something. I don't want you to say it out loud. It does change. But is there something that's consistent about it?
About the direction.
About the direction of the acceleration? Yeah.
It's positive because it's going counterclockwise.
I'm not understanding what you're saying for a couple of reasons. But
No.
I want to know the direction of the acceleration. In what direction is the acceleration?
Is it going towards the center of rotation?
Why? You guys should listen to this table back here. They're saying things that make some decent sense. Yeah, they're saying some things that make some decent sense. If you draw that force at any given point, and oh my gosh, oops, that was not very pretty, but you get the idea.
That makes sense.
The force is pulling which way? In, because that's the only one we got. Okay?
The yo-yo seems like a prisoner for the string. It just wants to go do its own thing, but the string is limiting its possibilities.
You know,
A free individual.
Cole, what I'm going to say is very positive, but I'm gonna put a little thing in there. Sometimes when you say things, I'm like, oh gosh, what's he going to say? Like, how far up on a tangent are we going with this? What you just said there, though, is absolutely accurate and is absolutely relevant, and I'm super excited about it. Can you say it one more time?
The string is limiting the yo-yo's possibilities in life because it just wants to go do its own thing, but the string won't let it. It's like a prisoner.
Yeah, it's like, I want to go this way. No. I want to go this way. No. You know what I'm saying? That's exactly what's happening. There's a force that keeps pulling this thing in, that keeps it in towards the center. If we cut this string, where's it going to go?
Wherever it wants to.
Not where, no, okay. We have to be careful. Because, friends, the yo-yo does not have free will. The yo-yo is not alive. The yo-yo is an object.
You ever seen Toy Story?
Nope, I want you to be quiet.
Yo-yo, huh?
I'm just saying. Like, I'm just looking at the clock at this point, friends. Okay? The yo-yo can't go wherever it wants because it's going to follow Newton's first and second law. But if we cut this string, we can tell, because we're physicists, because we understand the science, we can predict exactly the trajectory of this yo-yo, can't we? Yeah. At any given point, if the string broke? Absolutely we can. What would the direction be? Describe it for me. Tangent to the circle, and what's it going to do? Is it going to curve around? So let's say that the yo-yo is here at some point, and we cut the string. Is the path going to be like that, like that, like that, or like that? We'll call it A, B, C, or D. That's why I'm asking the question. Talk to your table. Figure it out.
Once you cut the string. It would see it.
To the B or C. Might be D.
All right. It's one of the four. You got a 25% chance. Except that you know physics. And if you use your physics, you should be able to figure it out. Okay? I was just talking to my physics kids about this too. Sometimes your brain wants something to be true. You have to step back and say, is that really following the laws of physics though? Or is that just like what I think should happen? Because sometimes there's a difference. Is it going to be A?
No.
I don't hear people yelling A.
Hey.
It wants to be away, right? Is it going to be D?
No.
So maybe B or C.
C.
So some people want to say B, want to say C because why?
I said use on the like the chart.
C doesn't curve. C's curved.
C's curving. And it was curved, it was going around in a circle. Curvy, curvy, curvy. Life is good, right? But what, Kate?
Oh, I don't know. Why is if velocity is perpendicular to the tension, shouldn't it just go straight in a circle?
Yes. You're right, because you're using physics, right? So the rule is that if there's no net force acting, is an object going to accelerate? Let me say that again so you catch it. If there's no net force, will the object accelerate? No! And if you look at this, if we take the orange one away, you've just got these two forces. We're assuming there's no friction. Is the object going to accelerate? No! If it doesn't accelerate, that means it has to have a constant velocity. And if its velocity was in this direction, it's just going to keep on going in that direction, isn't it? It's going to keep on going. So that's the way it goes. Just like this. It would just keep going that way forever until it hit something. Okay? A lot of times people want it to be C. People want it to be C because it looks like it should be C, right? Because it's going in a circle. But you have to use your physics, not just your gut feeling. Jasmine, what's up, babe? Did you have a question?
Yeah.
Okay.
So if it were not on the floor and you were just spinning around in the air, it would go out to the side first, but then it would, what was it, projectile motion again?
It would exactly do projectile motion, yes. That's exactly right. Did you guys understand what she said? So,
It's on the floor, it doesn't fall in the
right, so if we draw the water cup, that's an upside down water cup, but I kind of screwed it up. There we go. And it's got a velocity in this direction. Friends, if it's got a velocity in that direction, and so now just to be really clear, we're not on the floor. Here's the ground. And it had a velocity. We did this problem in September, right? Here you go. You've done that problem before, right? That's just plain old projectile motion. That's it. So it just go, yes. And you could figure that out. And so if you were given a question where it said that you were whirling a cup of water and then we cut the string at the top, where would it land? Could you figure it out? Let me ask you this way. Do you have the physics tools to figure it out?
Yeah, we have that poster.
You have that poster, so you can, I don't know, I feel like the poster doesn't really,
Remember that when we took the test on it?
no.
That's alarming.
Because it takes a lot of effort to look at that poster and figure out what's going on.
You would have noticed this, like, now you got mad.
Or I would have just been like, why are you wasting your time? Because we only have 40 minutes to take a test. You know,
But
whatever.
Got, like, completely.
All the equations are on the sheet anyway.
Right, exactly. All right. So we have now established one very, very big, important thing. Okay? We have established that when something is going around in a circle, it is always accelerating, and it's always accelerating toward the center. That's important. Okay? The acceleration when you're going around in a circle in uniform circular motion. Uniform means that it doesn't change. That means that the speed is constant. Circular motion that the object, stay with me, you guys. The yo-yo is always accelerating because it's changing direction, and it's always accelerating towards the center because that's the thing that's pulling it in. And there's a fancy word for towards the center. And this is so important. It's so important that I want to make sure that you're really with me right now. The word for towards the center or center seeking is centripetal. So uniform circular motion results in centripetal acceleration. Now, this is very important. If you ask people about this, okay, or if you ask somebody to, you go up to your parents, you're like, hey, look at me, I'm whirling some water, and you ask them to draw a free body diagram, they're like, what are you talking about? But if you ask them if there was a force going up, they're going to say, yeah, there is, right? Because everybody wants there to be. But it's not there, and you know it's not, right? There is this super, super big misconception out in all of the world. What's that? That's why I'm teaching this to you. Go forth and tell people physics. That's what we're doing. Okay? Here's the deal. The force that causes uniform circular motion is always center seeking. It's always a centripetal force. It has a P in it. Okay? True story. This morning, I was at jazzercise. Okay? We were spinning these weights in our hands. And I told the instructor after, I was like, I'm teaching this tomorrow or today, and I'm totally telling my kids, she's like, oh gosh. Anyway, she's not a physicist, so it's okay. We're spinning these weights, and we're going like this, right? And she's like, you've got to use, and then she said the F word. 5:30 in the morning, and she said the F word at me. I was like, are you serious?
Tell us the F word. I want to know it. What's the F word?
I will say it one time, and I don't ever want to hear it in my classroom.
Flamingo.
Do you understand? Because if you start using it, it's one of those slippery slope things. Oh, I'm just going to say it once. No, then you just start saying, and then it just goes out into the world again, and that's not what we need. Are you with me?
Yes.
So I will say it once, and then I'm going to put a big no sign through it because it's wrong. Here's the thing. You ask my jazzercise teacher, you ask anybody out on the street, and they're going to use the F word at you, and it's bad. Holy bananas, don't do it.
So no pubes are allowed in the classroom.
Okay? That's the F word. Centrifugal means center fleeing. It means center fleeing.
It should be called centrifuge.
Okay? Is there a force that is, we'll talk about it in just a second. Hold on a second, okay? Is there a force that's pulling out? That's causing an object to go out? No. Yesterday when we were drawing that free body diagram, you wanted there to be because your gut feeling says there needs to be, but then you think about physics and you say, oh, that's not right. There is no force pushing out. Anytime you have circular motion, the reason the thing is going in a circle is because you have a center-seeking force. You have a center-seeking force. You have centripetal acceleration. We're going to do the math with it tomorrow, and I'll show it all to you tomorrow, but the thing I need you to know today is that it's centripetal. Okay? You've experienced this more than once in your life, I am sure. One example is when you're sitting in the back of a car, somebody goes around a curve. Are you with me there? And it feels like if they go too fast, like you're being thrown out. Do you know what I'm saying?
Yeah, I do.
Now, here's the thing, friends. Stay with me because I want to make sure you understand this. I want you to think about it right now. As you're going around the curve, it's like you are the yo-yo. Are you with me there?
Yes.
You are an object, no free will now. You are an object, and you want to go in a straight line, right? You're an object with velocity. You're just going to go unless something acts on you. Unless you have a force, a net force, that's something other than zero, right? As soon as you have that force, you're going to accelerate. What causes the force that makes you feel that when you go around a curve? What causes that force? It's got to be something, though. You have to be able to name it. You're going around that curve. You're in the car, right? You're not driving because that would be super dangerous.
Force of the earth.
No.
Air resistance.
Think about it, guys. I want you to think about it. You know this. You can do it.
Normal force.
Gravity.
Now you guys are just yelling forces. I want you to think about it. Friends, okay, so that's what everybody's going to say. I'm going to tell you what Cole just said, but I'm not going to attribute it to him because I don't want you to know that he said it. He said, it's the force of you being thrown against the car. I want you to think about this, and I want you to imagine, not with your 7 brothers and sisters in the back of the car that are pushing on you. If you are in the back of the car by yourself, you go around that curve, it feels like you're being pushed out. But is there anybody pushing on you? Is the car pushing you out? No.
Is in fact
Is the car there?
No.
Yes. And is the car pushing on you?
Yes.
Which way is the car pushing on you?
Towards the center.
It's pushing you in. If you tried to go around a really fast curve in a Jeep without doors, where would you go?
On the ground.
The same direction that the water would go if there's no bottom to the cup. Are you with me there? It's the same thing. Okay? You would just keep going in a straight line because there's nothing pushing on you. There is nothing pulling you out. That's not true. You with me? Okay? The normal force pushes you in, and thank goodness for that. Because if the normal force was not there,
What if I want to keep going down the street?
right? I'm going to give you one more because we've got a couple minutes. I'm going to give you one more. Here it comes. You're going to write this down because this one's good. How many of you have been to Adventureland or another theme park? Anybody?
Yep.
One of my, well, it's not really my favorite ride, but it was really sad when they took it away. The what, Elizabeth, what were we talking about?
Silly silo.
The Silly Silo. How many of you have ridden the Silly Silo or something similar?
Yeah, yeah.
All right, so you've done it 7 million times. I was talking to one person in my other class. It's like, I rode it 12 times in a row when I was like 8. I'm like, that's disgusting. Anyway, for those of you that have never ridden the Silly Silo, if you've never ridden it, let me describe it for you real quick. You wait in a long line. When it's your turn, you walk into a room. It's just a big circle. It's a big cylinder. Okay? You walk up and you stand against the wall. Like, this is great. They close the door. They push the button to turn it on. And what happens to the room? It starts to spin. And it starts, so one thing at a time. Hold on. So it starts to spin and spin and spin and spin and spin. And it gets up to a certain speed. Are you with me there? And then eventually, what happens to the floor?
It drops.
It drops. And what happens to you?
You stay to the. You don't stick to it though.
But you don't fall down, do you? What forces are acting? Gravity is acting. Let's draw a picture real quick.
When it goes, it goes.
There's way more to that than we're going to talk about. So there I am. Oh, my legs and my body have been disembodied. That's kind of sad. Whatever. Yay! All right, friends. Shh. I got 2 minutes and I need them because we need to do physics. You got one force. What force is acting on you?
Gravity.
Okay, which way is it pulling or pushing?
Down towards the earth.
Got it. There's no floor. Just want to make that really clear. What's another force acting? The force of the wall? Which way is that one pulling or pushing, Liam? Perpendicular to it because it's a normal force, right? So it's pushing you in. Absolutely. What else is pulling or pushing? Because the net force here would be going this way, and then I would fall. But I've ridden this ride, and I don't fall. What other forces are pulling or pushing? There is friction.
Oh my lord.
Friction always acts which way?
Opposing the motion.
Opposing the motion. Where's the motion going to go? Where would you go without it?
Down.
Down. So friction goes up. Friction also always goes parallel to a surface, right? So friction's got to go this way. So you don't fall because you've got friction, and you don't go forward because you've got the normal force pushing you in. All right. We'll do math tomorrow. See you tomorrow.
Yeah, would you just go towards the left?
So if I just like